So this is one. So this is actually a talk at the ICRA. So at the recent conference, I just thought that these are already well polished slides, so I could just piggyback on them and I don't have to prepare it. I mean, I have my presentations are always have a lot of equations and things, but these are actually nicely prepared, which are more uh, has a bigger reach than some of my presentations. So I thought let's just present. So these are all prepared by the students. I mean, I'm just using them. And this is a joint work with the Venkat, who is uh, one of my collaborator at Clemson. He's a faculty at the automotive. Right now, we have this two department merging together. I mean, already merged. We have so he's both me and him are at the School of Mechanical and Automotive Engineering, and Ajinkya, Chinmay, Tanmay, these are the PhD students. So, I mean, as I was saying, I think this is basically about off-road autonomy. How to do, yeah, how to design vehicles that can navigate in this off-road environment. So, yes, as you can see, the title of this presentation is Digital Twin meets the Koopman operator. So, essentially, what we're doing in this is actually we're using the digital twin model. I'm going to present the results on this presentation is mainly on the digital twin use of the simulation data in the form of digital twin to construct the Koopman operator and show this autonomy. But we have used this even in hardware setting. Okay, so like which I'm not going to talk today. So this these are model-based approaches shows promises and the first principle modeling, white box. The model that we end up using have some advantages that they are explainable, you can actually interpretable, and you can analyze them. Uh, Data-driven modeling, capture modeling dynamics, uncertain variations, and so on and so forth. Dignity, quality, quantity. And so, as I said, I think like whatever we have done so far, I mean, one could just think of that as a nice pipeline uh, to develop these Koopman models from data and then use them for planning and controls problem. So easier said than done. It's a lot of painstaking efforts. So one of the challenges, let me just get to the challenges, which may not come. I can use this to show what are the results we have. But a couple of challenges that we face is actually how to use this, how to design these lifting functions, right? So you get the linear model in the high dimensional lifted space, but if you use the wrong lifting functions, you're not able to actually the model that you end up getting actually are not good in terms of prediction or control. So what are the right lifting functions one could use? Now, especially for this vehicle dynamics one, of course, again, this is sort of very problem specific. For the vehicle dynamics one, uh, basic simple. We started with simple models like bicycle models, which are sines and cosines sort of nonlinearities. But then we look at the Lie derivatives of this vector field. So think about you have a original system as exploitable f of x, okay, and then um, plus g of xu, right? Now you can actually you can just look at the nonlinearities of f of x and g of x and put them in the basis functions, right? So that's one way of doing it. What you could also do is you can actually compute the Lie derivatives of f and g. That basically tells you the direction of like controllability in different at any given point. What are different directions in the state space that are controllable, and then as you take higher and higher derivatives, you get more and more controllable spaces. Less like what you do like in linear systems, b, a, b, a square b, and a n minus 1b. Similarly, nonlinear version of that will be the Lie derivatives of f and g and higher order Lie brackets. So you could use the nonlinearities coming from this higher order Lie derivatives as a part of the basis functions. Okay? And that was one thing actually which gave us some interesting results. So that is where actually we use some of those basis functions coming from not just the nonlinearity coming from f of x and g of x, but the higher order Lie derivatives of f and g to lift this nonlinear system from data. Okay? Um, so that's the basis functions part. I think what you see here is kind of a complete pipeline. So where you actually starts with the so another thing which is so here you start with like a digital twin framework. You have the some state estimation thing, and then the data from the digital twin is what is used to collect the this is called multimodal data collection, and what is used to actually build the data driven models. Okay? So another thing which is different than what we have studied, what we have learned over a series of lectures when it comes to the Koopman model is that in this case, we didn't come up with a one single Koopman model. Okay. This Koopman model, we're kind of actually parameterized model. So instead of coming with one Koopman model, we have a family of Koopman models. Just think of them as like a, instead of one linear system, we have a piecewise linear system. So there is some, in this problem, the curvature, which is a geometrical feature, like you have some reference path and you want to actually follow. So the problem here is that you are on off-road terrain. You have some reference trajectory. You want to go from point A to point B, following the reference trajectory the best you can on this unstructured terrain. Right? So this reference trajectory is characterized using some curvature. Along this reference trajectory, the curvature keeps on changing. So when we collect the data to learn this Koopman model, we actually use that parameterization to collect, to construct this model. So these models are actually not one single Koopman model, but a family of Koopman model, where the parameterization for this family is actually the curvature. Okay? So we use this family of Koopman model in the setting of the MPC, and then MPC and is you guys we already talked about that the MPC formulation. Then so the data is first collected with which is already parameterized with different curvature, and that data, the parameterized data, is now used to learn the different A and B matrices. Okay, and then identification of A and B matrix again follows the same procedure, just a least square problem that we did. Again, the lifting function, as I said, were based on the not just the uh, nonlinearity in the vector field, but it was based on some the Lie brackets, Lie derivatives, Lie brackets to compute this higher order nonlinear terms, which are then incorporated in the basis function. So these are the two main uh, sort of the characteristics when it comes to the modeling of the Koopman for this application. And then these models are actually used to uh, so you have this family of Koopman model, and then you want to follow a reference trajectory. You want to so you know there's a reference trajectory a priori. So what you do is that you use this you you run these n models. So let's say there are n models. You run these n models and see just from the point of prediction, even without the control, which of these n models are actually comes closest to the reference trajectory. Okay, like in terms of prediction. So if you look at the prediction error of this n models with the reference trajectory and see which of this n model gives you a smallest error, and then you pick that particular model to do the MPC control in your MPC loop. So that's where the optimal motion planning and optimal local planning comes. So if you look at a local planning path, then local planning path, you actually pick a appropriate Koopman model based on a prediction error. So whichever model gives you a less prediction error, you use that model within your MPC to design the optimal control. So there is some online part, there is some offline part. So the column on the left is actually all done offline. So where you actually collect the data offline, you build this family of model offlines and so on. So the optimal control part is all online. So you do it in real time. The part of the motion planning is part online, part offline, because the online part comes from the fact that you actually do this prediction in real time based on the then Koopman model and see which one actually comes closest. That is actually online. But the training of the model themselves, the computing of the then model, which are used in the path planning, these are all offline. Okay, so uh, And yeah, so you have this. So in digital twin, you can create these different environments, and you can actually collect data in these different environments. So here we are particularly interested in an environment which is actually changing, which is off-road. And then so this is the digital twin of some terrain which is outside the lab, outside the campus, outside. And this is how you collect the data. They're actually playing with joysticks and with a simulator to collect this data. So we have this the synthetic environment, and we have this digital twin for data. So these are all the state data, and these are the control input data, right? So there are the states. These are the some specification on the number of trajectories they are generating and the frequency at which they are uh, collecting this data. Uh, so the data for the state and the inputs are actually has to synchronize. This is what I was telling you about. It takes a lot of efforts. I mean, initially to sort of collect all these different data and train these different models. Hmm. And then, yeah. So now this comes an important piece, and this is sort of what I spoke to you yesterday too. I mean, maybe I could elaborate more because I think this I feel is um, a very neat way of actually extending the applicability of the Scoopman when it comes to not just robotics application, but I mean any other application. So the in this case, as I said, I mean you have the system model, but then which to some extent is actually very well understood model, vehicle dynamics model. It's not like that complicated. But the main challenge actually is in capturing the interaction of that model with the unstructured environment, right? Now, how do you actually capture that interaction, right? So, and especially, I mean, there are detailed simulations models which are actually developed to do this, but those models are not that particularly useful when it comes to control design. So we wanted a model which is actually at the right fidelity, which is could be used for the purpose of control. So the idea that we come up with is that just like we have the effect of the control input sort of captured in this. So what you see here is z of t plus 1 equals a kt zt plus b kt ut, right? So this kt is the parameterization I'm talking about. As I said, we have not just one A-B matrix, but we have family of the A-B matrix. And then and that the which A you choose depends upon this factor kappa of t. Of course, here he is writing it as a kappa of t as if it is continuous, but in reality it is discrete. We have only discrete families. So kappa of t can take, let's say, only finitely many values. So depending upon the let's say if kappa t takes only n values, then that means you're choosing one of the n models. Okay. So if kappa t is 1, then that means you're using A1, B1. If kappa t is like, let's say 5, then you're using A5, B5, right? So there's like a finite family of models. So that's the parameterization part. And then this A and B part is the A is the system dynamics part and the B is the control part. So that is something that we have already done. But now to capture the interaction of this vehicle with the environment, we actually introduce this augmented B matrix. The second B matrix, BG of X. So this G here is the external forces which are acting on the vehicle from the terrain, okay, which we don't have the first principle model with. But what one could do is that we can let the vehicle run on different terrains, okay, and so we can actually measure this ground reaction forces, which are with some sensor. That means those are like the G, and then we can actually try to identify a model from data. By that I mean identify the B matrix, BG matrix from data, which will actually best explain this this data set, right? So what you have in this, you can have measurements like you have the state measurements, you have the input measurements, but you also can access to a disturbance measurements and use those in a part of the training of your A, B, and BG. Okay, so this is what I think is kind of was a new thing, which is how do you actually capture this terrain interaction through this augmented B matrix. Okay, And once you actually do that, then again you can actually set it up as again a simple least square problem. So just like we can actually lift the Koopman states and without lifting the U control input, we can identify the A and B matrix. We can also identify another B matrix, which actually uh, helps us understand the effect of the external forces, uh, which are not control forces, which are sort of disturbance forces on this model. So I think that was another interesting feature of this. Now you can imagine that you have some camera, you can actually look at some, uh, you have some preview, and then you could use that information in the identifying these external forces. Um, Yeah, and I think these are all the details of the terrain heights, the gradient vehicle. So the global mission planning, terrain heights and gradient vehicle constraints and limit obstacles and restrictions. So you can incorporate all these things in this. So uh, this is the part which I was talking about in terms of how do you pick this appropriate Koopman model based on your prediction error. So whichever model gives you smallest prediction error, you can pick those A and B matrix and then use them as a part of the MPC. So this is sort of a mathematical way of describing how to pick this model based on the prediction error. So you compare the prediction error with all the N models, and whichever is smallest, which is the arg min, you pick that field. Uh, and then you do and then you do the optimal control. That's the MPC problem. And these are some of the. So this is in the top. You see the deployment in the off-road uh, simulator in the auto drive, the simulation environment, and in the bottom use that thing. And can you see that? I think I have a hard time seeing it here. And these are basically some more qualitative metrics of the performance. So I think you see, so this is what happens when you actually don't have that augmented term uh, in the model, and then these are the first column is for the like the error between the simulation and real in the absence of the augmented term. So you can see that the errors are larger, and then use that augmented term, the error actually. So this is the additional augmented term which are introduced that significantly reduces the error. That you should be adapted. So, so anyway, so I think this is one thing I want to talk about. I mean, want to present. As I said, this is mostly sort of developing this end-to-end pipeline, which based on a Koopman theory, which can take data, simulation data, or even experimental data, uh, and develop this Koopman model and use them for controls. As I said, I think this is all very problem specific, but there are two main things that has actually come out of this, which I sort of conveyed to you. One is that how do you choose these basis functions? So you have, so that's something that you could perhaps see for your own research. Maybe that could be useful. Second is the uh, the modeling of the interaction of the vehicle with the environment itself. So that is actually taken care of with the with this additional matrix P. So let me see. I think we have. And let me see if I can show. Yeah. So this is. We have also used the density planner on on our quadrupeds. Uh, so so this is some Yeah, so this is like I think one of the challenge. As I said, I think in the quadrupeds, I think there are control of quadrupeds is much more challenging than just the vehicle dynamics. So here, the density function, which I just presented for safety, is used for doing some of this footstep planning problem. Okay? So that's what you see here. So we could take that density function and not that I mean we cannot do it in other methods. There are other methods out there which can also be used to look at some of this planning problem. But we were just wanted to use this density function for looking at this planning problem. Okay? We can actually take this and kind of implement this. I don't have any videos for the. I may have to dig in, but I don't have any videos to show to you on how we have used this to do just a simple MPC. It's not very um, it's not very surprising because I think the MPC stuff is so robust. You could actually use any other method. In fact, you could just use linearized based MPC, and that works on a quadruped, especially on the flat terrain. So it's not a big deal. I think uh, uh, the the obstacle avoidance and the footstep planning, I think, is are some of the two things where we are trying to use the density based approach. Okay? Um, Again, this idea of actually um, using the augmented matrix in the Koopman setting to model the environment, which that is something that we are trying to do incorporate even in the even with the quadrupeds. Okay. Um, yeah. So I think that's all I have to show for this. Any questions? Maybe we can just stick to this so far. Any questions on this? Hmm? Good. Yeah. So these are again some. Yeah. So this is this is a little old work. So off-road navigation using Peron-Covinus path plan. So this is again density-based path planning for the quadrupeds, and then we apply Koopman MPC for the low-level control. This is sort of this is not using very low fidelity models. They are not really captures all the details. But yeah. So here you again here we're doing the path planning, the high level path planning using the density function, and the low level controller is using the Koopman. Anyway, so I think this is the theory part. So let me now jump to this. I mean, some other applications in robotics has to do with uh, doing safety in the presence of adversary, right? So the problem is the following, like where you, uh, yeah, where you want to actually, right now when you're doing the safety, all the problem was specified in terms of going from the initial state to some target set while avoiding some unsafe state. But imagine now that there is an adversary which is actually trying to push you towards the unsafe set, and the control is actually trying to keep you away from the unsafe set, right? So these problems can again be like formulated. I mean, that require little more like efforts to write these things down. But I think we have some work again using this Koopman theory to look at these kind of problems. Like how do you look at safety in the presence of adversaries? Okay, so this typically reduced to some differential games problem, and then you can write down the um, mm, so when it was control design problem, you can write optimal control design problem. We write them then as a Hamilton-Jacobi equation. Now, in the presence of adversary and the safety, you write them as a Hamilton-Jacobi Isaac equation. So, I think those are the other things that you could do. Um, I think another problem that one could think about in robotics is to do with the and that's not just with the robotics, but also in power system, is the problem of uncertainty propagation. Or you have some, and this problem also has connection with this safety problem. Uh, how do you actually use this Koopman methods or the linear operator methods for uncertainty propagation in dynamical system, right? So, uh, so um, as you were saying, um, so let's say you have some x dot equals f of x, like even in the uncontrolled setting, and you have some initial uncertain initial state. X0 as rho of x, right? So rho 0 of x, right? And you want to propagate this forward. Okay. Now, how do you actually use this uh, linear operator methods to do this? And it's very natural because how does rho 0 propagates forward? Rho 0 propagates forward by the Perron-Frobenius operator, right? So this will be a rho 1 of x. Okay. Um, Now you can do a finite dimensional approximation of P, and then you can propagate the uh, uh, rho 0 to rho 1, right? But alternatively, you can actually also propagate this using so-called moments. You know what a moments are? Like, so if you give a Gaussian distribution, then a Gaussian distribution is characterized completely in terms of the mean and the second moment, right? So if I give you a mean and second moment, you can consider Gaussian function. But if you have a if you have some arbitrary probability distribution function, let's say, for example, rho 0 of x, which is the initial density function, you will need infinite moments to actually express the function. Okay? Because the rho 0 is infinite dimensional functions, infinite dimensional object. Uh, so to so to so rather than propagating this density function, one can also propagate moments of this function. Okay. So while the density is propagated using the Perron-Frobenius operator, the moments can be propagated using the Koopman operator because of the duality. So what do you mean by moments? So uh, let me see if we can do this. Okay. So let's say I want to compute the moments of of rho of x using in terms of this basis. So what is how do you compute the moment? So you basically compute this integral. Um, okay. So you have, let's say, mk0, which is psi k of x, rho 0 of x. So these are the moments with respect to this basis function at time 0, where rho 0 is your distribution of the initial condition. And then these are your basis functions. So now you want to know how this mk0 propagates to mk1. So how are these moments propagating? So what we are doing now with this is basically, instead of propagating this infinite dimensional object rho 0, you are propagating only the finite dimensional moments or finitely many moments, right? So m1 0, m2 0, and so on to mn 0. So these are the finite moments you want to propagate. Now, what will be the mk1? Right? So that will be your psi k of x p rho 0 of x dx, right? So because what is mk of 1? Mk of 1 is actually the moment uh, computed with respect to the rho 1, right? So this is your rho 1 of x. Okay? This is the propagation of rho 0 to rho 1, which is using the Perron-Frobenius. Okay? Because as I said, the densities are actually propagated forward using the Perron-Frobenius. So this is what this is. Now, using the duality, this you can write it as u psi k of x rho 0 of x dx, right? Because of duality. Okay? And so you basically have converted this problem of propagating densities to propagating moments, where the densities are propagated using the Perron-Frobenius, and the moments are propagated using the Koopman. So this is how we can actually write down and now this is for one. Similarly, for mk at some time step L will be simply u L of psi k of x rho 0 of x dx. Okay. So L here is a time step. Okay. And now you can again do the finite dimensional approximation of this Koopman and write down a K matrix and then propagate this, write this down as a finite dimensional problem. Okay, so this is how one could actually do the um, uh, uncertainty propagation using these operators. I think I'm almost coming to the end, I think, of this. I mean, one thing which I haven't really talked at all throughout these lectures is how does all that we have done so far actually carries over to systems with uncertainty, right? Where you have some noise in the system, some stochasticity in the system, and the nice thing is that everything that we have done carries over smoothly to system with uncertainty. So we can define this Koopman operator, we can define this Perron-Frobenius operator for system with uncertainty, both in discrete time and continuous time. Not only that, um, even the control problems also generalize very nicely in the stochastic setting. Um, I mean, I could talk a little bit more about that, but I think that's um and in fact we have some papers on that as well. But I'll keep it I'll keep it brief. So what I want to do now, maybe I can give some references because I think some of these things have been missing from this. So let me see if I can point to some of the good references on the So the Lasuta and Meke book, I think, is a very good book to start with. We've already given a reference for that. Um, and I think the one reference which, yeah, so this one is a good reference. Um, this is a good one because I think it not only stays in the function space, it also goes back to the state space and explain how the connection between the states, whatever you learn in the function space, how it connects to the state space, right? Okay, so this is in the Nonlinear Science journal. You can just Google this. Science, I think 2020. Okay. The classic reference um, on the EDMD. So those who may be interested, I think that I'm just trying to look for the classic reference on EDMD. Okay, can just do this a paper by Clancy. Yeah. So the classic reference on the EDMD is I'm still if I get some time over the next few days, I will polish those lecture notes I gave you, and maybe I'll put these references there as well, just in case. This is a paper, multiple authors on this. So I'm not going to write all the names. I'll just write the first name, Matthew Williams, and a few others. So this is actually in Journal of Nonlinear Science. Um, yes, this is 2015. Okay. Now, if you are interested in little more uh, convergence or theoretical analysis of this, then this is one of the good paper uh, on the convergence of extended dynamic mode decomposition. By Milan. This is again in Journal of Nonlinear Sciences, 2018. Then on the control side, you have uh, like the Koopman MPC one, right? I think yeah. So that is the reference linear predictor for nonlinear dynamical system. Nonlinear dynamical system. An operator means MPC. This is in Automatica and 2018 again. Right? Which will be a good other reference. So, um, and of course, there are many other ones. I just gave you the basic ones. Um, of course, there are a lot of like lecture videos by uh, on Koopman, right? I'm just trying to remember the name. Okay. Yeah, Steve Brunton and Nathan, right, on this on Koopman for control and modeling. So you could take a look. So let me and the we should give some classic references to. So this is like the own work of Koopman back in 1930. Uh, it's called Hamiltonian Systems and Transformation in Hilbert Space. By this is the National Proceedings of National Academy of Science, right? PNAS. Is the and then I have my own references on the control side, right? So the dual framework I talk about the Lyapunov function. So I think the one is that Lyapunov measures, which is a 2008 reference for almost everywhere stability. This is 2008. Um, it's a IEEE transaction automatic control paper. Uh, and then more recently, we have this control using densities, right? So the dual formulation of control using densities. So that is this paper. Uh, Convex approach to data-driven optimal control. Using Perron-Frobenius and Koopman operator. This is again 2000, 2022 paper. Again, IEEE tag. Okay. Um, and more recently, I have this paper on Koopman meets Hamilton-Jacobi, or when Koopman meets Hamilton-Jacobi. Hamilton and Jacobi. This is a 2025 paper. It's again in IEEE tag. Yeah. And of course, there are very, I mean, on density side, right? So I just the density safe navigation using what the title? Safe navigation using density function. This is in robotics later. This is IEEE robotics later. Okay. I mean, this list can keep on going. I mean, I think there's no, yeah. You can use this as a starting point and build on this. I mean, if you in future, if you have any questions on any of these papers or any of the things that we discuss, I mean, feel free to write to me. I will try to respond as I get some time. And if you want to if you feel some of these ideas were interesting, and if you want to pursue some of them in for the future, uh, yeah, we could certainly talk about these as well. Okay. Um, I hope you learn something from this, and I think you'll take some of that with you and use it for your research if you feel it's something useful. Okay, I think these are very powerful methods, especially, and I think kind of I'm reiterating some of the things which I've said right at the beginning. I think some of these are some very powerful methods, especially as systems are becoming more and more complex, and you have an opportunity in the form of having a lot of data. So I think it's the right time to use this. I think the whole idea of like thinking of models uh, as linear operators, I think that's you don't have to kind of stick to this idea of you using model as a differential equation or model as a simulations, but one could think of this linear operator as model themselves, right? So I think with that, I can end this. Okay. Thank you.